So as I was saying, the Bohr model had some really great points to it. However, it didn't solve the problems that the physicists, remember the dramatic physicist, pointed out, like the collapsing atom paradox. So why do the negative electrons stay where they are instead of coming into the positive core nucleus? And then a few other things, but most importantly, the failure of the Bohr model and the Rydberg equations and the such is that it only worked for hydrogen. So it could not explain the theory of multi-electron atoms. So when you start adding more and more electrons, what happens is those negative electrons repel each other. And so the theories that Bohr and Rydberg predicted only worked when there's a one electron system. However, there are pros. So he did correctly theorize that the energies of the electrons are quantized, and those levels are dependent on the principal quantum number n, and that energy is involved in moving an electron from one level to another. And so the forms of energy, such as heat and electricity, that we covered in lab, does cause the electrons to become excited. So we need a better theory, but this was a great starting point to quantum mechanics. So the first issue that quantum mechanics had to overcome is, does the electron behave as a wave or does it behave as a particle? So we think classically that electrons are particles. However, de Broglie suggested that particles actually have wave-like properties, and they experience diffraction just like waves. So there are two types of waves. So interference and diffraction. What is interference? So if we have two waves, two light waves coming in, if the amplitudes, so if the peaks and the troughs overlap, then the intensity increases, right? And so they add. However, if the peaks and troughs are opposite, so if the peak is here and the trough is here, when you sum them together, it becomes zero, and so they cancel out. And you can read more about this in your book. So that is interference. And you can have constructive and destructive interference, and they don't have to be exactly overlapped. Sometimes if you can overlap slightly, then your peak can increase or decrease slightly. And we talk about waves. What we're really talking about are the standing waves. Now, traveling waves is probably what we think about in the ocean, where the node, and again the node is the location where the amplitude is zero. The node moves, and so we call those traveling waves. In a standing wave, what you see is the node stays stationary, but the amplitudes can change. So if you've played a string instrument like a guitar, the length is the same and you can pluck it, right? And when you pluck it, you can have the node here, but the amplitude could be positive or negative. And depending on how you pluck it, you can have multiple nodes. But the length of the wire or length of your wavelength stays the same. So the n remains fixed. But what does that mean for us? So, let's say you have a guitar. The wire length stays the same, right? You're not going to add wire, you're not going to subtract it. It is fixed. But depending on how you plug it, you can have one peak, or one peak and one trough, or two peaks and one trough, and so forth. So the amounts of notes are different. So let's put an electron in there. And again, you're not going to have half. So the peaks and troughs is an integer number. So 1, 2. And the wavelength, so distance between two peaks or two troughs or two nodes, is dependent on the length. So the length matters, the amount of nodes matter. However, when you put an electron in there, the electron is not going to stay stationary. It's going to move, right? It's going to move back and forth. So you also have to take into account the momentum. And that is where de Broglie's wavelength comes in. So if you think about, instead of saying you have a guitar string, let's say you have an electron moving around a nucleus, and that length is fixed. It does have a particular wavelength, right? Because we know that the wavelength is dependent on the length and the integers. However, it also has a mass and velocity. So we have de Broglie's wavelength, which is equal to Planck's constant over momentum. Now, this V, and this is very, very important, this V is not nu, okay? It's not the Greek letter nu, and it's not frequency. It is velocity. Notice how nu is like a V in, in the wave, so it's kind of italicized. This V is not, okay? So that is one of the main problems that people get confused about. V and nu are two different variables. So we've seen a few equations for wavelengths. It is important that you know which one to use at what point. So if a problem asks you something to do with de Broglie, you have this equation. Or if your problem has something to do with momentum, you know to use this one. If it's given the length of the string, or the length of a molecule or something like that, you have this equation. But we can use these equations, plug them all together, and find something very interesting. So we have the equation that relates the length and the nodes together. We have the equation that relates the momentum of the electron. We also have what we call the kinetic energy. And we'll learn more about the kinetic energy in later chapters, but that's just the energy associated with moving an electron. And so if we add all these together and sub them in, what we find is this equation. We're not going into how to derive this equation. That is for quantum mechanics, which if you take physical chemistry 2, you'll learn more about that. What I require you to know for the next test is the de Broglie wavelength equation. Okay? The other equations will be given to you. But what we can learn about this is, or why this equation is important, is that it tells us and relates the energy to the principal quantum number n. And so we saw before the energy levels, right? So we have the ground state, we have a ground state, and these excite states. And what we see is that they're not evenly spaced, because the energy is associated with the quantum number squared. So the spacing increases as you increase the number of n. The most stable energy is the lowest one, and that's what we call the ground state. The energy, now if you plug in values in the n, where n it has to be 1, you see that the energy cannot be 0. Hence, the atoms cannot collapse. So this solves the collapsing atom problem that the Bohr model did not. So how does this all relate? So we can look at the wavelength, so between the two peaks, and we can look at the frequency. Now, we know that frequency and wavelength are inversely proportional. That means as the wavelength increases, the frequency decreases, or vice versa. So we see here that the longest wavelength would be B. So we know that the answers have to be C or E. Comparing A and C, A has longer wavelength than C. So C has the highest frequency, but lowest or shortest wavelength. So the answer is C, where C has the shortest wavelength, A has the next, and so B has the longest wavelength, but lower frequency. So we learned a lot today about wavelength and energies. The take-home message, and this is very important, is that quantum mechanics is complicated. Because when things are super small, so the size of an electron, we have to think outside the box. And a lot of the theories that we learned from classic mechanics, we cannot apply to how we visualize an atom. So just because you have a negative electron and a positive center does not mean that they're going to attract each other. And that's due to the equation we saw before with energy. We also know, and this is slightly covered in your books, it gets a little complicated when we talk about the momentum and mass of a particle. So, or location, I should say. So the Heisenberg uncertainty principle, you do not have to memorize this equation, but you should be familiar with the theory, is we cannot accurately predict the momentum of a particle and the location or position of it. We can know one or the other. And again, we're not going to go into the theory behind this in this class. That is for the certified majors who have to take PChem 2. But you are expected to know that we can't know the momentum and position at the same time very accurately. So to see the electron position, we have to probe it with radiation or some sort of energy and change its position or change the velocity. We can also change both of them. And so we can only specify the highest probability of where an electron is in an orbital. So we don't know where the electron is. However, we can guesstimate, and for quantum mechanics, we can estimate the probability of finding an electron in certain locations. So the bottom line in the take-home message is that we cannot determine with any degree of certainty the momentum and the position of electron.